Oh, I know why. Because once I close my laptop, it just disconnects and it just stops that. Sorry. I do need to remember, I need to re-recording it. Okay, cool. So let's imagine I've only got one single hypothesis, and let's call them HBAT, right? And I assume it to have a test error. When I say test error, I should actually just call them expected risk. Okay, so whenever you see me writing test error, it doesn't mean that from the data set, you're the ones you pick for your test error. It's actually all the data that's made, right? So you have an expected risk, which is greater than epsilon, right? And right, for that particular hypothesis, you know that the expected risk is going to be greater than epsilon. Okay. Now, in order for, remember, when it's not in a version space, it has to have what? Everything, your empirical risk has to be zero, right? Empirical risk has to be zero. So otherwise, it's not a version space at all. You can't really even talk about it's being epsilon exhausted, right? So now we know that it's definitely going to have having a expected risk greater than epsilon. We need to work out what is the probability that its empirical risk is zero, right? Okay. So what happens? How do you calculate the probability of an empirical risk equal to zero? Is the probability that every single pair of data has been classified correctly. Yeah, which means that another way of saying that is the loss for every single pair of data is zero, right? So which means that this satisfies simultaneously as this and this and this. So all your M data are classified accurately. I mean, I shouldn't really say classified because we haven't talked about what kind of model it is. It could be a regression. Right? It just means that you have zero error that's coming from every single data point simultaneously. Okay, so they all should satisfy. Okay, and then this probability is less than that. How do I get that? How do I know that? This is going to be less than that. I mean, I says equation 15, but what does equation 15 try to say? So before we talk about this, does anyone know why it's actually one less than epsilon? I mean, going from here to here is easy, right? You can sort of see it straight away. But how do I get from here? In fact, I mean, how do I get from, this is m of them, so that's why you have raised to the power of n. But why is one of them less than 1 minus epsilon? No suggestions. Let's have a look at 15. All right. So you know that we know this, right? This is our assumption. If you are given that particular hypothesis, HBAT, we know that the expected risk is going to be greater than epsilon. Yeah. So we do know that the probability, in the sense of the data, that's the stochasticity comes in, the randomness comes into the data, right? We know the probability of misclassification is going to be greater than epsilon. Yeah. So the probability of correct classification is going to be less than 1 minus epsilon. Yes. Okay. So for this particular hypothesis, which in general have a misclassification greater than epsilon, right? Alternatively, it says the expected risk is going to be greater than epsilon, implies this. It also implies this. The correct classification is going to be less than equal to 1 minus epsilon. Right? The correct classification is at most 1 minus epsilon. Okay? So take a look at this to tell me if that's your concern to you. Actually, I made a mistake in this notation here. Can anyone sort of see it? Yes. That should be a expected risk. So that should be empirical. That's the whole thing is the expected risk. But the things inside the expectation has to be the empirical risk. Okay. That's what I try to. Okay. Cool. So you know that for a single data to have a correct prediction is actually have at most this probability. Yeah. And if you have m data, it should be raised to the power of m. Okay, so you have m data should be raised to the power of m. So that's how I get this. Right. So it's 1 minus epsilon raised to the power of m in here. Okay. And so why is this less than that? Why is this less than that? I mean, in fact, we can just drop n. Like just look at that. So 1 minus epsilon is going to be less than exp of minus that. Yeah. So that's something that's kind of given. Oh, sorry, another mistake. X minus, sorry, x, just x. Okay. So you all know that, right? It's 1 plus x less than 1 plus x divided by 2 raised to the power 2, and that's going to be less than 1 plus xn raised to the power n, and when you let n equal to infinity, it becomes exponential of raised to the power of x. So if you let this guy to be minus, if you let x to be minus epsilon, then you have an exp raised to the power of minus epsilon, and you raise to the power of m again, it becomes exp of raised to the power of minus en, epsilon n, sorry. Okay, so that's how you get that. Any concerns? So yeah, the way to see it is just let's drop m. So you know that 1 minus epsilon is going to be less than exp minus epsilon, and then let's raise both to the power of m. Okay, let's raise to the power m. That's to n. That's good. Okay. Yeah, apologize for that. That's a mistake. It should be this x. I will have my notes corrected after the class. Any concerns about this? Okay. So if no more concerns, we need to talk about this term. So remember, I said something about there's got to be exist. So at least some hypothesis where you have 0 expected risk, right? At least some hypothesis is going to be having 0 expected risk, sorry, empirical risk. And what does this one try to say? What's that? So when you actually multiply by that, this is all of it, right? Every single one of them will have expected risk of, so that's the union, right? So what I'm trying to say is that this is the probability of having the first data, sorry, her first hypothesis to have, sorry, let me draw it properly. So this will be, so the probability of hypothesis 1 to have 0, okay? And here's another one, is the probability of hypothesis 2 to have, empirical risk of 0. And here is the probability of hypothesis 3 to have empirical risk of 0. Okay, and you know that there's going to be at least one of them will have empirical risk of 0. So it has to be less than the union of all the three. Okay, so it has to be less than so either this or this and this, or some kind of a combination of this has to be less than the union of the three. Okay, right. So that's why you times by the number of this, because the probability is identical. So you need to times by the number of them. Okay, it's called the union bound. I know what you're thinking. It's very loose, isn't it? It's very, very loose. But that's how we do things in learning theory. Sometimes it can be very loose, especially when you have a union bound. But don't worry too much about. So when you see it for the first time, you go, that looks very, very loose. I mean, this union is actually huge. Right? But yeah, that's how a lot of the bounds are actually derived. So another typical example you will see in a lot of the literatures is this: the max of a set. Max operator is sometimes very hard to deal with. What do you think is the appropriate bounds for the max of a set? And assuming that xi is actually going to be greater than 0, non-negative sets. It's a set of non-negative numbers. The maximum of a set of non-negative numbers. What do you think it's the bound that people use this very often? The sum, thank you. So they use the sum, okay? And sometimes you think, that's just a single element, right? And this is a lot of elements together. But that actually simplifies things a lot because it's a lot easier to deal with the sum than the max operator. Okay, yeah, so sometimes when you sort of see this kind of union bound for the very first time, you go, that's, but yeah, after a while you will get used to it. So any questions about the derivations? And now after you deriving this, then that's it. So you basically have this thing, which we have talked about them before. You get this, okay? Now you get this. Okay, so once you get that, which is good, you can actually bring the m on this side. So that's just simple math, right? You bring them this side, you take the log on both sides, and you actually deriving this equation, right? You're deriving this equation. That's what we had before. So we know that, this is how many pages? 4th page. We are going really well. So we are now actually having this kind of a relationship. We know that if you fix your epsilon, you fix your delta, you do know how many of the m, which is number of data you need in order to cater for this particular value of epsilon and delta. Okay. So in many cases, you will find the m function is actually written in terms of epsilon and delta, which is that, which is something that's of this form. So people love to, some of the papers are actually written in this kind of form. But yeah, just reflect that. Okay. Any questions about this? Before we go on, talk about the generalization error. Okay, no questions? Okay, no questions, then we will move on. So this is important. This is something that you do need to remember. Okay. Okay, so let's move on then. So the next bit I'm going to talk about is the generalization error. So generalization error, before I talk about it, I need to talk about, we're going to use something called Halfting inequality. Like I said, I'm not going to derive it for you. But Halfting inequality is used a lot in learning theory. So what it says is this. If you have m, in this case, I have n. If you have n ID samples from a distribution, with known mean. Okay, the mean is mu. And I do know the range of each of the random variables. Okay, so in some cases, for example, I mean, the cases that I'm going to show you is that the empirical risk. So by the way, the empirical risk that we have just calculated, what is its range? So that particular definition of empirical risk, we just talk about it like what's the smallest value you can have and what's the largest value you can have. 0 and 1, right? 0 and 1, okay? Because you're taking the average. So just imagine in situations where we do know the range of those random variables, sorry. And we know that you have n ID copies of them. This is the concentration inequality using the Hofstadter inequality. Is that okay? Let's take a look at this equation for a minute. So n is the number of data points you have. B and A are the range of your random variable, right? It can't actually be larger than B. It can't be smaller than A. And by the way, it doesn't actually, yeah, so it comes smaller than that. And this is the concentration inequality. That's its bound, okay? So I think if this is the first time you see like a real concentration inequality, remember at the time I just sort of say, this is an epsilon and this is a delta, right? But this is your delta, okay? Can I just sort of, for you to see, this is the function of epsilon. Where is epsilon here? So epsilon is in here, right? So epsilon, do you see epsilon here? Epsilon is in here. So if you change the value of epsilon, your bound will change as well. So if you say let epsilon equal to 0.01, and you can substitute 0.01 in here, you can calculate the bound, okay? Can you verify this? How do you verify that? Experimentally. I mean, you can derive it. That's what Hofstadter lemma, Hofstadter inequality tells you. But how do you, so just imagine if you wanted to verify this thing empirically, assuming there's a lot of computer science students. I think last time I checked, there's 0 computer science students. But if you know how to program, how do you verify something like that? I mean, all you need to do is to draw lots of samples, right? And then to calculate the sample average, right? And you do know the distribution you're drawing samples from. So therefore, you will be able to, and you can just nominate like an epsilon. And then you can start calculating how many of those samples are greater than epsilon. And then you can divide it by the number of samples you have drawn. So you can actually have this probability. And then you can just calculate this. You can just using whatever, like MATLAB or Python or R to calculate this quantity. And you will see, you will actually see whether this probability is actually going to be less than that, right? Okay. Well, I mean, if you have nothing else to do, maybe you can empirically verify your Hofstadter inequality. Okay, but trust me, it works. The derivation is correct. So how do you actually using your Hofstadter inequality in this particular case? So what's this and what's that? Like what's mu and what's your sample average? So what's the sample average here? Obviously, the sample average, they are corresponding to your empirical risk. And this is your expected risk, yeah? And we also, people have also told me that your By the way, which one is a random variable? This one or this one? Your empirical risk is a random variable, and the stochasticity comes from the data, right? The sample data you actually draw. And this is a constant. It's an expectation. Okay. And we also know that the random variable is actually from a range between 0 and 1. So you can simply substitute this being 1 and that's 0. That's how you get that, right? And so this will give you m, and that will cancel out to give you this. Yeah. And once you get something like this, you do know that, yeah, so that's how you get that, all right? That's how you get this, okay? By using union bound, which we just talked about just then. All right, so let's keep on going a little bit. We let this to be delta, right? And then we will solve this. And then you will know m is equal to that. So if we look at m in this form and compare, so let's just have a look. Just like put that in your mental picture for a couple of seconds. So this time around, we do have the square terms in here, right? We have the square terms in here. So this is 2 epsilon squared. And if we look at what we had before, we have epsilon. Right? We have epsilon. Otherwise, they are identical. So which one is better? Which bound is a lot tighter? Do you prefer to have epsilon, or you prefer to have 2 epsilon squared? Let's think about this. Remember, this quantity is your lower bound for the number of samples you should have, right? So should you have epsilon, or should you have 2 times epsilon squared? Which one do you prefer? Just epsilon, right? Of course, just epsilon. Because if you think about it, if you let epsilon equal to 0.01, and you know, I mean, you have still this quantity here, but just imagine this is a 1, right? You're actually going to get 100 data in order to get this thing to work. But if you have this kind of stuff, you're going to get, well, 5,000, right? You're going to get 5,000 data in order for it to work. So this is a much tighter bound than using halving inequality. So one of the things that people have to be aware is that because of concentration inequality, you have the less than equal to, that actually gives you a lot of creativity, right? And sometimes I mean, this is not entirely accurate, but I think, you know, when you're deriving a generalization bound, I would say this is the artistic area of mathematics. Because when you have less than equal to, you don't need to get exactly the same answer, right? But for a lot of the traditional models, people are competing against each other to derive the tighter and tighter bound. Okay, especially for very common models, because everyone tries to derive the generalization. And by the way, a lot of these derivations, you have to use certain assumptions, right? In order to using certain assumptions, you will be able to deriving much tighter bound. And so yeah, that's another avenue where a lot of machine learning theory people are actually working on. All right, cool. So yeah, that's a generalization bound. And let's just keep on going. We actually put in this form and you bring them over in here, and then you will derive the epsilon is in this form, okay? So what I'm trying to say is that what you can do is this. Remember, we have sort of, I'm just going to say P of X, right? You know, greater than epsilon is less than 1 delta. So you can do two. Well, maybe what I will do is I will use another form. So when I have something like this, I can either put delta as a function of epsilon, right? That's what we have seen before in this form. So in this form, this is the delta. So this is essentially delta in a function of the epsilon. But we can also do another form in actually keep delta here. We will make epsilon in terms of delta. So here's an example of how we make epsilon in terms of delta, right? So you can see now epsilon is a function of delta. The delta exists, right? But we need to get rid of epsilon. We need to write them out as a function of delta. And the reason of doing that is we can sort of say with the least probability, with the least of 1 minus delta probability, this guy is actually going to be done by that. And you can see delta is in here. But epsilon is gone because this is epsilon delta. Okay. Is that okay? So, yeah. So, but by the way, if I write them out in terms of probability, how do you write them out? So that's the probability of R H minus, so H, right? Less than equal to this guy here. Maybe I'll just say like this guy, okay? This guy here is going to be greater than 1 minus, right? And as you can see that this bit here is epsilon into the function of delta. Yeah. Is that clear? By the way, I don't mind to go through them again because that's kind of important. Not that it will appear anywhere else of this particular lecture, but it's important. I mean, this generalization bound is very, very important in machine learning theory. In fact, it's also important in machine learning application, which I'm going to show you in a minute why it's important. So yeah, like I said, this is just different ways of how you're writing this, right? With at least 1 minus delta probability, this is less than that. Or you can just write them out in the traditional way of probability of this thing greater than 1 minus delta. Or the probability of this thing less than that is going to be greater than 1 minus delta. They're exactly the same thing. Okay, so I want to ask you a question, right? So when we talk about learning theory, what's the advantage of deriving something like this? I mean, typically, this form may be slightly difficult for you to see, but typically we actually bring this guy to the right. So we have expected risk less than equal to empirical risk and minus some kind of quantity, right? Epsilon H, right? Some kind of quantity. Yeah. So not H, I mean, delta. What's the, so is I mean, apart from the analytical power that this kind of bound will give you, right? It actually tells you how well does your hypothesis generalize to unseen data, right? It tells you that. Apart from the analytical power that it gives you, what else does it give you? So when you train your model, what do you use to train your model with? Empirical risk, right? Sorry, what were you trying to say? Yeah. So if you try to apply an algorithm to train your model, what are you training your model with? Which terms do you train your model with? You are trying to train your model with your empirical risk. Yes, right? Okay. Can anyone sort of give me an example of how you train your model with your empirical risk? Remember your binary. So remember your cross entropy, right? Your cross entropy of what? You have your cross entropy, right, of your model, okay? And so I'm just going to say that the model and your X, okay? And here is, so maybe I'll write them out more generically. So you probably have like a loss function, right, of your hypothesis, of your X, and your Y, okay? And then this is I equal to 1 to n, 1 minus n. Remember, this is the objective function that we have been talking about. Yes? I mean, that's the kind of function that you're more familiar with, except I don't call this h, I just call them, you know, some kind of f theta, right? But, you know, they're the same thing, right? F theta. And you want to minimize this. And by the way, this is your empirical risk. Yeah. It's just that today I'm using a simpler empirical risk. I'm replacing this with, you know, 1 of hypothesis of not equal to yi. Okay. But you know, that's just another generic way of writing this. Okay. This may not be just for binary classification, but that's a generic way of writing this. Okay. So when we try to minimize, we're going to say arg min of theta of this. Essentially, we try to find your empirical risk. Yeah, that's what we try to do in machine learning. Okay. Do people remember, what if we try to prevent overflow? Sorry, overfitting. I don't know why I say overflow, but what do we do when we try to prevent overfitting? Hmm? What? Penalty, yes. Regulator. Right. We put a regulator. So we put a regulator. What kind of regulator do you remember we actually put in order to prevent overfitting? L2, no. Yeah. Usually square because it just makes derivative a lot simpler. L1 is actually for sparse solution. So we put a penalty to it. So we hope by putting in this penalty is actually going to prevent overfitting, right? But it is good. What other regulator can we put in order to prevent overfitting? Okay, so here comes a bit of the magic, right? Just imagine this bounding quantity here is also a function of h. Then what? So your expected risk less than equal to empirical risk plus, plus. Y for minus I. So imagine that I have your expected risk less than equal to empirical risk plus another bounding term. The bounding term also contains h. If you can prove this, what's going to happen? And remember, your empirical risk is the thing that we try to, it's your objective function. Okay, you try to minimize. And then you will adding some kind of a regularizer to prevent overfitting. Well, what if
you have, if you can derive this relationship, what if you can derive this relationship? What if you can derive this relationship? And H is in your bounding terms. Look at this. Any people trying to be brave enough? If that's the case, this is your regularizer. You don't have to use this. Why? Because this regularizer guarantees it will reduce overfitting. Why? Because by minimizing that, because of this relationship, so you will minimize the difference between your expected risk and your empirical risk. Okay, so that's a much better regularizer to use because it guarantees if you can prove this. If you can prove this, your bounding term must have your hypothesis in it. Then you know that for whichever hypothesis you are able to obtain, this bound exists, right? So it will reduce the discrepancy between your training and your testing error, i.e. the discrepancy between your empirical risk and your expected risk, okay? And by the way, this is what a lot of machine learning people try to do. If you work on theory of machine learning, that's the kind of stuff that you will be doing. So for this particular subject, I mean, all I can do is just to introduce you to those some basic concepts. And hopefully some of you may end up doing some machine learning research in the future. Okay, so it's a good time to have a break. And when we come back, we only have a few slides. In fact, we only have like 1 page to go. So I think we will probably spend 30 minutes to talk about empirical risk minimizer, sorry. Empirical risk minimizer, and then we will finish for the theory part of your subject. Okay, so if you find today's lecture a bit conceptual, don't worry too much. Like I said, this will be the first and last time you will see learning theory. So from next week onwards, we're going to talk about something much more practical, like a Gaussian process, which I'm sure that you will learn a lot from that. Okay, so let's take a break. So please come back at 5:37. Okay, so welcome back. I think while I was having a break, I found this particular research paper for those of you who might be interested. So this paper was actually published very recently, like last year, and this is the best journal in machine learning, Journal of Machine Learning Research. Like that's the best journal. But if you read that particular paper, the central idea is basically what I just talked about. And if you're reading that paper, it basically just uses that. There's a bit of fancy terms in here, but ultimately, there's a different notation. This is just your expected risk, and that's your empirical risk. And this bound that you can derive it, which also contains Q. Just believe me, Q is your hypothesis. So you can sort of see that if you minimize these two terms together, it guarantees to reduce your discrepancy between your empirical and your expected risk. And that's it, right? So that's obviously the paper also extended things a little bit, but it's not no more than what I just described. So yeah. Okay, so that's enough said about this. Let's finishing the L pass. Okay, so the last one that I'm going to talk about It's called empirical risk minimizer. Sorry for the misspelling. It's actually empirical risk minimizer. There's an R, there's a risk in it. Okay, so here's a bit of concept for you. Just make sure that's okay. So there's a bit of concept for it. It's something called the realizable setting. So when you have something, it's called the realizable setting. So you can sort of assuming there is something from, there's at least, I think there at least one hypothesis from your concept set is actually going to map everything to zero error, okay? Is able to achieve zero error. But in the agnostic setting, that's not always going to be the truth. That's not always going to be true. So one way to think about it is that when people talk about agnostic learning, you kind of assuming there's a little bit of system error in it. System error like the ground, like the background noise, the background stuff. You can never map everything perfectly to zero. It just can't be done. Okay, so that's called the agnostic learning. So when you performing something like this, okay, when you're performing something like this, this is in fact what you can learn from your algorithm. What you can learn from your algorithm. So remember, do people still remember this notation? HSA. So this is the algorithm, right? This is the algorithm. That's the sample. And that's the hypothesis. So when you put these three words together, what does that mean? When you have three words, like H is hypothesis, A is algorithm, S is set of training data, your sample set. What does that mean? Again, we just talked about 2 hours ago. What this means, you are using that algorithm, like gradient descent, to and apply on this sample in order to obtain a hypothesis. Like that's the best hypothesis you can learn from using this algorithm, and you actually from this sample. By using different algorithm, you probably will derive different set of hypotheses. Okay, by using the same algorithm, you probably will derive different hypotheses, but that's why it's actually belong to a set. So basically, these are the algorithm you were using, and you apply them onto this set of samples. You're gonna derive this particular hypothesis. Okay, what I'm trying to say is that using the same algorithm, you may not derive exactly the same hypothesis, but but this is one of the hypotheses this algorithm we were able to generate. Okay, right. So this is actually learned from what? Like this is depending on what? I mean, let's forget about the algorithm for now, but it's actually depending on the set of samples that you have, okay? Now, once you have learned something like that, you want to compute the expected risk, right, of the hypothesis you have learned. Can I just ask, which one is going to give you more error? So if you're actually talking about your expected risk for this, or you talk about your empirical risk for this, sorry, it's H. Which one is going to be bigger? Is your empirical risk going to be bigger, or your expected risk going to be bigger? Your expected risk will be bigger. Why? Because that hypothesis is actually learned from the sample you are given to, right? Therefore, you can hypothetically train a very good model that satisfies all of your data in the sample, but it may not work in real life. Therefore, your testing error or the expected risk is going to be greater than that. Okay, because this is tailored for this sample. It's not tailored for every bit of data. Right? So maybe let me draw a diagram. So you probably learn something like this that goes through every single data point. Okay, and that probably will deliver you with a zero, training error. But it's not going to be possible if you apply them to data in general. So this will be larger than that. Okay, so it's going to be larger than that. All right. So, and remember, anything that without the hatch, these are all expected risk. Okay, these are expected risk, and the H star is the best expected risk you can possibly have. So H star is the best expected risk you can possibly have. We don't know that because we can't see every single bit of data, right? Therefore, you do not know what H star is. There's no way you can obtain that. But let's just assume it is like the best hypothesis you'll be able to get if you pump in the world's data in it. So let me tell you a little joke. Not really a joke, because it's a real. When I was in Sydney, Sydney also has a Google office. Yeah, I think they have about 900 people, mostly engineers. Or some people are sales, especially for Google Cloud. Anyway, so I had I know someone really well. So he invited me to go to Google, and we had a chat with him and also with the people in his team. So at the time, they were asking me about something that I do for out of distribution modeling. So there's another branch of research in machine learning. So I kind of said, look, I talk about things like, I said, you can't have all the data in the world, right? Because that's why you can't assume that all the data are actually inlines, because you do not have access to all the data in the world. And then this is where this guy said, maybe Google, we have all the data. Obviously, that's an exaggeration, but Google obviously have more data than most other companies. So anyway, just assuming that in more realistic setting, no one has all the data in the world, and the things that you can learn from your sample is only tailored for the data that you have in hand, right? So that particular hypothesis, that green line, maybe deliver very, very low, empirical risk, but the expected risk should be high, okay? And so what you wanted to do is that in the agnostic setting, remember I said, when I said agnostic setting, you won't be able to find, a hypothesis that's going to give you zero, testing error or zero expected error. So therefore, there's always going to be a little bit of system noise in here, right? So hopefully, what you wanted to do is that you want this guy that you've learned from your training, from your training data, to actually have a very low expected error, right? That expected error is the minimum of the possible expected error. So that is the minimum possible, in the comma, expected error. The minimum possible expected error, and plus some kind of absolute. Okay. In a realizable setting, the assumption is that the minimum possible expected error is zero. Okay, you will be able to find a hypothesis that goes through every single piece of data that's going to deliver you with zero accuracy, zero error. Okay, so that's the realizable assumption. That's the agnostic assumption. Okay, so the last one I wanted to talk about, it's just notations. So I don't really have an example for you, but just remember that. And the last, and again, that's a thing that you do need to know is when there's a lot of people actually talk about sample complexity. Sample complexity is where, remember I said, some papers love to write them out like, this is the algorithm, that's the concept set. Some papers like to write them out in this, right? Or some papers like just to write them out as epsilon and delta, but other papers write 1 over epsilon and 1 over delta. But they're the same thing, exactly the same thing. All right, so what you wanted to do is to say that what kind of M, what's the lowest number of training data I need to have in order to generate this type of epsilon and this type of delta, okay? So refresh your mind a little bit. Remember today, what did we talk about? PAC learning, right? What does PAC learning try to do? What's PAC? What's the probable? The probable is delta or epsilon. Delta, right? The least 1 minus delta probability. The discrepancy between training and empirical risk and expected risk is going to be less than epsilon. So epsilon is approximately correct. Okay, approximately correct. So probably approximately correct. PAC. Yeah. I mean, you have to kind of read the notes again, maybe multiple times to fully grasping the idea. But that's it. That's it. It's not harder than all the epsilon delta stuff you've learned in your other mathematics classes. Okay. All right. Okay. So by the way, the last term that you need to learn is the sample complexity is to actually just work out what is the minimum number of data points is able to deliver that particular delta and epsilon. Okay. All right. Cool. So yeah, I'll talk a little bit about the empirical risk minimization. So as you know that this will be the empirical risk minimize. This will be the empirical risk minimizer, right? So using that particular algorithm, sometimes people just get rid of that. They just call them like, you know, H, S, and star. It's the same thing. When you want to make the H specific to a particular algorithm, you put A in it. Or sometimes people just leave out A. Just say that's the best training hypothesis that I'm possibly able to deliver. Okay. So just imagine that we have proved that with the least probability, this absolute value is less than epsilon divided by 2. And this stuff less than epsilon divided by 2. Okay, just imagine you proved this already. Because remember, epsilon is a function of delta, and delta is a function of that. Okay? Just imagine you have derived that relationship already. Okay. T of R S, sorry. You have already derived that equation, T of absolute value of that minus that. Okay. Okay, so basically that's what that says, right? So just imagine you've derived that. And can I I think people might be worried about this epsilon divided by 2 part, right? Why is the epsilon divided by 2? By the way, this is entirely arbitrary. This is entirely arbitrary. You can have epsilon divided by 3 because it doesn't matter. If you choose epsilon to be 0.01, you can also choose epsilon to be 0.02, then divide by 2 to be 2.01. Okay. So can people sort of guess why if you're reading some papers that people mention epsilon divided by 2? Just so that after all this manipulation, the final result you're going to get is epsilon. That's it. So that's why they start with different fraction of epsilon, so that the final result will be epsilon. By the way, this is also the case in here. Okay. So, all right. Just imagine you can prove this. Now let's actually have a look at these terms. Let's just be very sure what are we talking about here. What does this guy mean? So what's this? So we have this term, this term, this term, and this term. They're all different. So what's this term here? This is for arbitrary H, okay? For any arbitrary H. So this is like for all H, for all hypotheses. What's this? That's the empirical risk, right? For all H, for all hypotheses, empirical risk minus the expected risk. Okay, right. Yeah, okay. So this is also empirical risk, right? But what's H star? H star is what? So what? Yeah, the best hypothesis in what? The best in the lowest expected risk. So this is very careful. You've got to be very careful, okay? So this H star gives you the lowest expected risk. So if that H star gives you the lowest expected risk, would that be low? Would this be low? By the way, this is empirical risk. So is this term going to be very low? No, not necessarily, right? H star minimizes your expected risk, but there's no guarantee that you will be minimizing your empirical risk. Okay? Because your data, maybe if you look at across all the range of data, yes, that's going to give you the lowest expected, but your data might be here. So it's not guaranteed that it's going to minimize your empirical risk. Okay. So what's this? This is your expected risk, right? So this term will be very low. This term will be very low. Okay, because this is minimizing that. Yeah. Okay. Okay. So is that clear? Are we all clear with these terms? Okay, great. So after we are clear with these terms, by the way, we just need to, like, all we need to do is derive in this, right? Because this also implies that. So if we say for all H, this is true, then that's also true. Because all we need to do is to substituting, like this term is just H, you know, we write them out, we write H in terms of H star, okay? So this is true for all H, but also true for H star. Yeah. Okay. So, you know, I mean, this kind of absolute value sometimes worries people a little bit, right? But that's why I'm writing out here. So if you know that the absolute value of X is less or equal to 1, does that imply X is less or equal to 1? Yes, you have to imply that, right? Because if you think about it, like 3 is less than 5. That also implies, 3, if that's the case, and 3 is less than 5, right? If this is less than 5, that also implies, so it's minus X is also less than 5, yeah? Okay. So if both X less than equal to Y and minus X less than equal to Y, that if and only if the absolute value of Y is X is less than 1. Okay. Cool. So you just think, you can substitute X with either 3 or minus 3. You can get that. Sure. Okay, so, right, once you actually have done that, then what we can do is that we can prove this is true, right? So why can you prove this is true? By just looking at that, right? So the absolute value is less than that. Then we know that, without the absolute value, that's also true. Okay, so without the absolute value, and we know this is going to be less than equal to this plus that, okay? Right? I mean, we're just using another form. We just sort of, all I'm doing is that because this is true, so we know RH, right here, RH minus absolute value is less than 2. And you know this is true, and we know this is true, and we know this is true. Okay? And all we're doing is that we substitute a particular H, which is the empirical risk minimizer. That's also going to be true. Okay? So once we have done that, and we also know this, that's true as well, right? This is just well, I'm not using that. I'm just, because this is for all H. Okay. So that's just the assumption that we have to start with. So knowing this assumption, we know this is also true. Okay, cool. So once I got that, how do I know this is also true? So how do I know this is true? So which means that I do need to know this is going to be lower than that, right? So why do I know this is lower than that? Exactly. So because this is minimized for my empirical risk, right? I'm always training it with my empirical risk. Whenever you're training an algorithm, you always try to minimize the empirical risk. So therefore, this stuff is your empirical risk minimized. So it must be the lowest. So it's going to be smaller than any H, including this stuff, right? Which is the lowest in terms of the expected risk. But who cares? As long as it's not this, it's going to be lower, right? In terms of its empirical risk. So that's also going to be true. Okay, so once this is going to be true, and you know this has to be true. Why? Because we just apply the same thing again, right? We the same thing again, okay? All we do is that we just apply the same H. Remember in this equation, they're identical, except the H that we are applying here. But now we actually change the same H, we also get that, right? And therefore, we need to add up this thing together, right? So, and you know, and that's why we are having this term and this term adding together. We're getting ourselves just epsilon. All right, that's all. That's all we are actually doing. All right, that's all we are doing. Yep. So basically, we're just getting this. You know, this is less than so. If you're still worried about that, I'm just going to spell out for you. So this is going to be less than RH plus epsilon 2 divided by 2, and then you plus the epsilon divided by 2 together, you get this epsilon. Okay, and that's it. So what I'm having now is this thing. I'm having my empirical risk. So whenever I get for my algorithm, I'm deriving my empirical risk minimizer. That's the best thing I can do, right? And I will be expecting, that once I substitute them into my unseen data points for all the data in the world, my expected risk is going to be less than. That's the best possible expected risk I'm going to get, and plus an epsilon. And that's based on the assumption that of this, if we can prove this thing in the first place, okay? And then we also have this relationship. Okay, so that's pretty much it for the 5.5 slides that I have for you today. And any questions? So hopefully we can have an advanced class. So this is like I think it's the machine learning foundation class, although it's called the foundation of data science. But if I'm gonna run an advanced science in a learning theory, then this will be the type of things that I will be talking about in here. And obviously, it's going to be a lot more than just that. So, not sure what would people think if I'm running something like that as an elective for postgraduate students, possibly for PhD students in the future. Okay, so any questions? We now have 15 minutes, so obviously. I would like you to so we need to make the best use of that 15 minutes. So you can ask me anything. from the previous class or about your homework, if any question that you want to actually ask me. Alternatively, we can keep on going with this. I can talk to you about the interesting stuff like a PAC Bayesian. There will be more equations. No, I'm not going to do that. So I'll leave that just as it is for the PAC learning. Enough for today, but I'm going to let you go. So any questions you want to ask? Maybe about last week's neural networks class, the homework, or today's class, or anything that you wanted to ask. I'll give you like 2 minutes to think it over. Maybe what I will do is that if you don't really have anything to ask me, I could have just gone and show you. So I think we have gone through this thing, neural network, rather quickly last week, because I think a lot of the things that it doesn't really need further explanation. But do we have any questions about neural network from last week? I think one of the things that I haven't actually gone through details is that the ReLU function, right? So if you talk about ReLU function, this is the function that you're going to have. So essentially, if anything that is negative, you'll map it out to 0. Anything that is positive, you will make them to stay as it is. So that's it. That's the ReLU function. That looks something like this. Okay. Can anyone sort of tell me why is this ReLU function better than the sigmoid function? Because ReLU is actually used for your. So this is the sigmoid function, right? So you know how last week when we talked about neural networks, this is the neural network, right? This is a sigmoid function. Or you can have a ReLU function as your activation. So compare the two. Why is this better than that? Yeah, the gradient. If you look at the ReLU function, you have 2 types of gradient. If anything in here, you have gradient of 0. Anything in here, you have a gradient of 1. So I think this is where people will ask me. The gradient 1 is fine. Everybody loves it. It doesn't explode or vanish. You multiply lots of 1s together, it's still going to survive. But what if you have a gradient of 0? You just need to have 1 gradient of 0 to wipe out the whole thing, right? The gradient, so close to 0. Yeah. The gradient, no, it's actually 0. It's actually the maximum. Yeah, so when you have a like we talked about before, right? So if you have if you have a sigmoid function, because that gradient is equal to, does anyone remember? That times 1 minus that, right? So which means that the max of your gradient for sigmoid function is 0.25. So, and if you multiply lots of gradient together, numerically, it will be very close to 0. But really, when one gradient is already 0. So why is this used? If you have some negative functions, if you have a negative value, you will get 0 gradient. So the reason why it's used is actually, remember, we are actually doing convolution. So when you are actually doing convolution, your gradient is a summation of all these values. That's actually the size of an image. So that's the size of an image. So when this is ReLU, and that might be 0, so only one term is 0. You have a summation of lots of terms in it. Okay? And therefore, as long as one of the terms is not 0, you're going to have a gradient. So this is how we're performing. Remember, we have a convolution neural networks. We have something like this, right? And when we're performing convolution, we need to shift this kernel or weight or filter to every single possible direction. And you need to perform your inner product, yes? And when you take the derivative with respect to this W, okay? When you take derivative with respect to this W, your derivative is equal to this. That's your derivative formula. Your divide by, take derivative with respect to every single value of your convolution kernel, you're actually gonna get a summation across all your pixels, all right? So if one of them is 0, it doesn't matter because you have a summation of a lot of them. So as long as some of the stuff actually survives, as long as some of the Z is actually gonna be, strictly greater than 0, you are not going to get a derivative, which is 0. So that's another advantage of having a convolution operator, is when you take the gradient, it's lots of those gradients add up together. And using ReLU is perfect. Can I also ask you about the computation factor? So when you're actually computing ReLU function and then computing sigmoid function, right? Sigmoid function is 1 minus exp plus minus x. And if you have a ReLU, it's just max of 0 and x. Which one is faster? Max is faster, right? All you need to do is like if x greater than 0, right? Is x, otherwise say 0. And this is, it has an exponential function in it. It's actually much slower. I mean, if you're only computing one function, it's fine, right? But you need to compute lots of functions. Right? So this is only using feed forward. Right? When you compute your back propagation, you need to calculate the derivative. Calculating the derivative for this is actually quite hard. It's actually quite computational. So therefore, I mean, you got to do that, right? I mean, it's like you got to do this and one minus that. So you have one extra operation than just computing this. So therefore, it's actually computational. Remember, you are dealing with lots of images and lots of operations. So therefore, it's actually one operation. I mean, this may not be that much. I think people said this is 6 times more computational than that. And in terms of calculating its derivative, it's 6 times. But when you have lots of things you need to compute, like one in 6 hours, the other one in 1 hour. So
That actually makes a lot of difference. Any other things that you want to know about the deep learning parts,
which we kind of didn't go through them in very fine details, because a lot of the material you'll be able to, it's actually quite self-explanatory. Unlike the learning theory, which I think probably need someone to explain it to you, then a lot faster. So any questions? Okay, so I'm probably not going to ask people to stay back if you do not already have questions. So how about this? For the next 5 minutes, if you have questions to ask me privately, it's the time to ask me. Or if you want to watch other people ask me questions privately, that's also fine. So do you have any questions? So how about this? You're free to leave unless you have questions to ask me. I'll be staying here for the next class comes in. So yes, please. Yeah, please. Okay. By the way, I prefer people to ask me questions publicly. Yeah. The function and the theory. Which one? Yeah, it's not differentiable. It's well, there's a bit of cheating there. So we will say at this 0 points, we will say equal to 0, but it's not real 0. So at this point, it's actually it's not differentiable, but we will typically treating this particular value having derivative of 0. So it's kind of an engineering yes. And you will see in deep learning there's a lot of engineering tricks that we will find. Very good. By definition. Any other thing you want to ask? Probably or publicly later. So I mean, the question is that is the class material so far so okay? I guess that's also a very open network. I don't expect to receive any answers. But yeah, so I think if you are interested to know what's to come, just have a look at the subject outline. It will specify very clearly what are the materials to come later. But for next week, we will be talking about Gaussian process. And we will be talking about, you can't talk about Gaussian process without talking about kernel. So we will talk about Gaussian process and how do you do optimization? How do you do regression using Gaussian process? Okay. And I think it will be a lot more practical than the things we talked about today. And it's also sort of shifting away from the actual application. Like when we talk about computer vision, not many people will be working on computer vision. So it's like natural language processing, but the Gaussian process is one of those techniques. I think even if you are not going to be doing a specific machine learning application, it's still a very good technique to master, because it's a very useful technology that you can apply them into various different things, including finance. So yeah, okay. So since I'm not going to be able to get any questions out of you, I will time's up. So enjoy the rest of the week and enjoy your assignment. By the way, next week, I do expect you to have lots of questions at the beginning of the class regarding the homework, not the assignment, the homework. Your assignment will be coming in week 7, okay? So by definition, there will be the 7th teaching week because we missed out 1 week. So I think this is the 5th week, teaching week. So it should be coming in 2 weeks' time. I probably will give that to you next week. If not, it will be the week after. So start thinking about who you want to be partnering your assignment with as well. Okay, great. I will see you guys next Monday.